Hi, let's do an absorption correction example. I'm connecting to a Windows computer through TeamViewer for this example, but this should work exactly the same for you as it does for me. I'm in the folder where we collected the data for this crystal, and I'm going to open the data set by double-clicking on the run file. Like we did in class, I'm going to go through the steps of peak hunting, lattice finding, integration, and so on. I won't cover this in so much detail because this crystal is a twin, and we're gonna go through that whole process in more detail in a follow-up video. So for now, I'm just searching for the lattice and so on. I'm gonna do lattice auto unit cell finding. I can see from these histograms that the crystal was pretty good quality, even though, again, we're going to find out later on it's a twin. But the peaks that are in the boxes, they're sharp, and that means the crystal quality is good. Okay, we'll close the eWalt Explorer. We're finished with the lattice wizard, so we're going to go to data reduction with options. Clear the data from the previous run. Say yes to that. Everything else here is fine. The background on these frames is pretty low, and so we can go with average background. And like I suggested before, I'm going to leave the outlier rejection on 1 for now until we're sure of the space group. Okay, I'll make a name for this. I call things Dan, and I number them. So this is Dan 1. I put space group on manual, and I'm going to hit finish here. This should go pretty quickly because it's not such a large data set, and it's a small unit cell, a small unit cell, and that means there's not very many peaks to integrate. Okay, the integration is finished already, and here's our space group determination wizard. I can click through all that stuff. We see that the RInt difference for monoclinic versus triclinic is not too big, so we should be okay with monoclinic. There's no centering of the lattice. You know, well, we'll go ahead with these suggestions. I'm not 100% that this is going to be the right space group, but ShellXT is going to help us with this anyway. We'll choose P21 because P21 upon M is very uncommon, but again, it hardly matters. The formula, it has molybdenum and tellurium in it. We're gonna double check on that, so I won't spend any time getting the formula right now. I'm going back to the experiment folder now. I'm gonna do a very quick solution to make sure that we do get the correct formula because we need it for the absorption correction. So I right-clicked on the ints file, and I'm going to open it in OLEX2. Under the work panel, I can pull down the solve button. I can solve in ShellXT. The solution is quick. Oh, okay. Well, this says P21 upon M it's the space group that ShellXT found anyway. What's going on here? These look like they're floating in space. This is an extended inorganic structure, and that means we need to grow it out maybe a couple times before we're really going to be able to see anything. Okay. This layer looks good. It's a transition metal dichalcogenide. This layer, I can see it has a tellurium in the middle where the molybdenum should be. So I will just select one of these, type name MO. Now it's a molybdenum atom, and we'll run a quick isotropic refinement just to make sure nothing is crazy here. It doesn't have to be good. We have 13% for the isotropic refinement. Uh, the ADPs on all these atoms are non-crazy, so we can be satisfied with this. I'm going to click OK over here in the toolbox work panel. Sometimes I have to click this a couple times. Watch the formula up here. As soon as this updates, you're good, and you want to make sure to notice the formula and Z as well. As long as you notice both of those numbers, then whatever you put in the Z prime box, it's not important right at this point. So we have MO2TE4 with Z of 2. I'll fix Z prime. I'll set it on 1 so that this formula makes more sense. It's MOTE2 with a Z of 4. We'll come back to our data reduction window. I'm going to click on the Refinalize button, which is the third one down. The first thing I'm going to do here is go to my crystal movie. I meant to delete this. Okay. So here's our crystal. You know what? I'm gonna unset my center calibration here so that we can set it together. Okay, this is what we find when we walk up to the computer. We can see that this crystal is a little bit off center. You can see it wobbling back and forth. So that's not good. It's going to make our job a lot harder. So we're going to calibrate the offset under the center calibration window. And I'm going to move these two sliders until the edges of the crystal line up on both sides. Do the same thing for the second offset. This one is a bit trickier, but I think I can see it accurately enough. All right, let's try this. We'll go ahead and spin the crystal around and make sure that the crosshair is tracking it correctly now. And this does look pretty good. Okay, I'm going to put one face of the crystal facing me, and I'm going to click on the corners of the crystal. And we can have as many corners as we want. It doesn't have to be 4. Then I'm going to turn the crystal by about 90 degrees from the previous view, and I'm going to do the same thing again. I'm going to try to click on the corners here, although now they're really hard to see. Okay, so we tried that. We have a crystal shape now. It came out pretty suspicious looking, but it's a start. So what are we going to do with this? I can see that one of these facets is actually pretty good. I'll try to select it so you can see. This one looks like it is just about parallel to the big flat face of the crystal. Big flat faces almost always will have small whole number indices. Other facets, it can be hit or miss, but the big flat ones almost always are there for a reason. So we'll go to this face. We'll check what the indices are right now. It has HKL 1.219. So that sounds a lot like a 001 facet. And I'm going to click on this, go to Custom HKL, type in 001. We'll see how the alignment looks. This is the facet that we're watching. It's actually off by just a hair, but it's the movie can be off by a hair, and it's unlikely that this is a big face with some oddball indices slightly off from 001. So we're going to leave it that way. There has to be a parallel face on the other side of the crystal. And if this is the 001 face, then the other one is going to be the 00-1 face. So let's take this big crooked one and rename it to 0, 0, -1. Okay. Now we have two opposite parallel faces. The other faces of the crystal, we can see that they're pretty far off right now. Let's take this diagonal one and just delete it and remake it. Or instead of deleting it, I'll use the distance slider. I'll move it really far out so that it's out of our way. And now I'm going to click in the... yours is going to switch over to drag automatically. I'm going to click in this window. I'm going to drag a bar until it's on top of a face of the crystal. I'm going to release here, right click in the window, and go to add face. Okay, and the indices of these faces around the edges, we don't necessarily need to get them right as long as we have the overall shape of the crystal approximately right. So now I'm going to continue adding more faces around the edges here. This one looks okay, but it's a bit crooked. We'll do the same as before. I'll just move it out and I'll put a new one in its place. Okay. Drag, right click, add face. I'm going to switch this over to, we'll call it real HKL. Add face. Okay, now we've got the crystal shape pretty well. Maybe maybe this facet on the top it's a bit crooked, so we'll fix this one. Okay, add face, real HKL. Now we have a few faces with stars attached to them. That means the face has 0 area or it's not being used, so we'll delete the starred faces. And now the last thing we have to do is get the thickness of the crystal correct. And this is definitely a bit of a guessing game. But I'm gonna pick our 0, 0, 1 and 0, 0, -1 faces. I'm going to move that distance in slightly. I'm not looking at the camera so much. Instead I just got an impression of the thickness, and now I'm trying to move those faces to match the thickness that I'm kind of guessing. If it was bigger, then we could try to match it to the image, but when the crystal is so tiny, that's hard to do. So I'm just trying to get the thickness about right. Okay, we have the shape now, so I'm going to go to Edit Formula. The formula is MOT2, like we checked before, and Z is going to be 4. Okay. I'm going to set mu in formula. Everything is done here, so I'm going to hide and exit, and I'm going to click on the Refinalize button. I'm going to change the absorption correction type to analytical. That's a little bit simpler than Gaussian, and it normally works well. I'm checking the lattice type up here. It's 2/m, which is monoclinic. That's correct. I'm going to change the output name. This was Dan1 before, so now I'm going to call it Dan1_core to indicate that we're applying a correction. And everything else here is good with the defaults, so I'm just going to click OK. Oh, you know what? We did that on automatic space group assignment, which is fine for this example, but just to do it the way you're going to want to. Dan1 core, same as before. Yes. search for space group, change it to interactive. Okay, now we get our space group assignment dialog like we did before. And this is all good, so I can click straight through it. Now I'm going to type in the correct formula here, which is MOT2 with z equals 4. Okay, so that's all finished, and now we have this set of dan1_core files, and these would be the files to grab to continue with your refinement, which I would suggest you do it in a different folder. Okay, that's everything for absorption correction. Thank you.